We have this useful device that's been invented called a phase diagram. A phase diagram is a graphical representation. So in other words, you have a set of axes that are showing something. It's a representation of pressure-temperature relationships. So on this thing, you're going to have temperature on this axis, and you're going to have pressure on this axis. But what it's highlighting is the equilibria between the phases of a substance. In other words, where does it shift from solid to liquid, liquid to gas, and so on. Here's a phase diagram for water. If you look at how the phases are laid out, first of all, this zone here, this is the solid phase. Over here, it's liquid. And so this is the boundary. This line here is the interface between solid and liquid. And then over here we have gas. So this is the interface between liquid and gas. This is the interface between solid and gas. Where all these things meet, this is called the triple point. When this particular temperature and this particular pressure are met, that's when water could exist as a solid and a liquid and a gas all at the same time. That's the triple point. If you're at 1 atmosphere, drawing a line over here from 1 atmosphere over, that crosses the solid liquid line at what we call the normal melting point. So we know that water melts at 0 degrees C. And water boils at, so that's the liquid gas interface, water boils at 100 degrees C. So this phase diagram tells us what's going to happen when different events occur. If my pressure and temperature were such that I was at this point and I just increased the temperature without increasing the pressure, I would go across a line that doesn't include liquid. The solid is going to turn directly into a gas. Well, that process is called sublimation. If I'm moving from here to here, well, that process is called melting. If I'm moving from here to here, that process is called vaporization. You can see that it's possible to undergo phase changes without increases in temperature. For example, if I have a liquid that's right here and I just make the pressure drop without changing the temperature, I will get that substance to boil. Here's a phase diagram for a different substance, carbon dioxide, with some of these numbers attached here. You can see it's the solid, liquid, and gas zone. The triple point temperature is 56.4 below zero for carbon dioxide, and the pressure at the triple point is 5.11 atmospheres. So it has to be pretty high pressure to make this into a liquid. At 1 atmosphere, its normal boiling point, or sublimation point really, right there, is 78.5 below zero. At something akin to normal room temperature, a little higher than normal room temperature, if you get the pressure high enough, you reach what's called the critical point. And up in this zone here, liquid and gas don't exist separately. You have this really high density gas. It's almost a liquid called supercritical fluid. I want to point out a difference between water and almost everything else. Nearly every substance on Earth has got a phase diagram that's like the one we saw for carbon dioxide, where this line that separates solid from liquid slants sort of towards the right. Water's different. That solid liquid line slants towards the left as you go up. So here's what this means. If I have water in the solid phase, ice for example, and I increase the pressure on it, I squeeze it, it changes into a liquid, it melts. Nothing else does that. If I have carbon dioxide in the liquid phase and I increase its pressure, it's going to freeze. This is responsible for the fact that water has more density as a liquid than a solid. When you compress it, you make it liquid. Nothing else works like that. And so that's why ice floats on top of water. Almost every other substance, when you freeze it, it doesn't float, it sinks. Let's take a look at this example problem, which is asking us what happens to CO2 during some events. Well, the first event is the temperatures increase from 92 degrees Celsius to 25 degrees Celsius at 1 atmosphere. Let's go back to the phase diagram for CO2 to answer this question. We're starting out at 92 degrees C at 1 atmosphere. So negative 92. So negative 92 would be about maybe here someplace. At 1 atmosphere of pressure, you'd be about there. And then I'm increasing the temperature, but the pressure doesn't look like it's changing. So I'm going up on the temperature scale, and I'm going up to 25 degrees C, which would be somewhere over here. So what's happening is I'm heating up a solid, then I cross this line, it's a phase change, I sublime it all, turn it into a gas, and then once it turns into a gas, I'm heating it up to my final temperature. The next question is what happens when the temperature is decreased from 31 degrees C to 50 degrees C at 6 atmospheres. Going back to our phase diagram, finding 6 atmospheres and 31 degrees C, which is about there, I'm going to decrease the temperature down to 50 below zero. So what happens is I move backwards on the temperature scale without changing the pressure to about 50 below, somewhere in there. That's my movement. So what's happening? I'm cooling down some gas till I reach this interface. Then it condenses into a liquid, and then I'm cooling the liquid down until I get there. The third problem asks us to figure out what happens when the pressure is increased from 1 atmosphere to 75 atmospheres at 50 below. So starting at 50 below zero and 1 atmosphere, which would be probably about here, I'm going to increase the pressure up to 75 atmospheres without changing the temperature. So now I'm making a vertical movement. I'm moving on the pressure axis without moving on the temperature scale, moving to about that point. My line isn't real straight, but what happens is a gas gets more and more dense. I'm increasing its pressure until we reach this interface. The gas then condenses into a liquid. The liquid gets more and more compressed as it goes up this axis, and then once again we reach an interface. And then the liquid becomes a solid. It freezes under this pressure and eventually becomes a cooled down solid. When you dissolve something in another substance, the boundary between the liquid and gas shifts down. Like for water, this is the water triple point diagram. This boundary here between liquid and gas, that whole boundary retains its shape but shifts down a bit if you dissolve, say, salt in the water. So that it moves down to this new location like that. Now here's what that does. First of all, it shifts the triple point. The triple point goes down here, which means that this interface between solid and liquid also gets shifted by dissolving salt in the water, or whatever. You can dissolve anything in the water and this will happen. Here's the effect that has on boiling point. Here's the normal boiling point, where the liquid-gas interface is met at 1 atmosphere. Well, that's 100 degrees C. That's where water normally boils at. But now, at 1 atmosphere, the boiling point is met at this new interface between liquid and gas. And that's farther over on the temperature scale. It's going to boil at some higher temperature. There's an increase in temperature that we call boiling point elevation, delta T of boiling. The same thing happens on the other phase change. This is the normal freezing point of liquid water right there, and we all know that that's at 0 degrees C. But with the line shifted over, here's the new freezing point, the new interface between solid and liquid. So this is all liquid now after the phase shift. So if we trace down, we're going to see that the freezing point actually decreases. So we've got another delta T here, delta T of freezing. The freezing point goes down and the boiling point goes up when you add salt to the water or any substance and dissolve it. This is why we put salt on the roads in the wintertime. Instead of freezing at 0 degrees Celsius, we can get it to freeze at maybe -3 or -10 or something like that. And that leaves liquid on the roads instead of ice, and it's obviously safer.